Okay, so let's start by saying I have to assume that you watched the video on pegboard. I don't have time to go through that right now. So if not, go do the pegboard video, and now let's go into the lab. Okay, so before we go into the lab, let's go ahead and learn a little bit. Now, normally we say that torque equals a perpendicular force times the distance. Well, down here, we could say that this is the force perpendicular, right? And let me see, so that would be theta as well. So the force would equal the force times sine theta. Easy enough. And if we call this the distance from the pivot here, I guess I should put d there, then we would say that equals F sine theta times d. But you know, in mathematics, we have the capability of saying that 2 times 3 times 4, which is 24, right? 6 times 4, also equals 4 times 2 times 3, which is 8 times 3. Now, I'm not doing that because I think you're silly and you need a little math review, except over here, couldn't we then say that F d sine theta is true? So what would be d sine theta? Well, here's d. Sine theta would be over here. Let's extend the force past the pivot like I did in the pegboard lab. If you didn't watch it, you have no idea what I'm doing here. This right here, I'm trying to get that as perpendicular as I can. Not sure if I did it or not. This is perpendicular. If this is d and this is theta, this is d sine theta, which we're going to call the moment arm. Pretending that the force can be anywhere along this line, we're going to call it the line of force or the line of action. And this is perpendicular to that line of action. So we could write torque as the perpendicular force times the distance, or the perpendicular distance times the force. Now, the technical definition, how we usually write it, is torque in AP Physics is R cross F, which this is known as a cross product, which is perpendicular components. Either one of these fulfills that. So now let's go back into the lab and see if we can find this moment arm. Okay, so here's our cast of characters. We have a wheel that I've already, I guess I could do that for you real quickly. And if you decide to do this in your classroom, if you don't do this step, it'll mess things up. So first things first, what the heck, we'll just do this all the way. So let me take off this mask. It's just blue tape, and so that's easy to take off. You will notice that it's gonna move to where this right here, it'll go to the lowest position. Where do you get these bike wheels? This one's all messed up. If you look real closely, it's not round, okay? So if that's the heaviest part, then I'm gonna put just a little binder clip on here. You have to figure it out, use different ones, figure out where it works. And now, let me move this over. Okay, so now, notice it's barely moving. So that means I have it balanced. Got lucky. You might need different masses in order to do that. So now I take the mass, I'm going to go ahead and put it. I will want this to be able to come all the way to maybe here. That will make it easier for the video. Okay. So now let me put this. Go ahead and get that on. And why blue tape? Because it's light and it doesn't add enough mass for me to have to add any more counterbalances. There are other ways that I try to do this that were just way too hard. So now I have a 500 gram mass put here, just wherever, and then I have a spring scale here. Now, first of all, so now let's get real close to the spring scale. I'm sure that looked good. So let me go ahead and, so now we look, the spring scale is basically zeroed, right? So now if I take this and notice that mass is down at the bottom, to wrap this around, this is again going to be hard because I'm doing this with one hand. So right now, notice the spring, the tension is slack. It reads 0 because there's no tension, there's no torque due to that weight. All it's doing is pulling straight down. It's not turning the wheel. But notice what happens. Hold on. Sorry. as I start to pull on it. I'm starting to pull on it. The weight is going up. As the weight is going up, the tension in the string is going up. Hopefully you can see the blue way over there. Okay, the tension is getting greater. Tension's getting greater. The tension's about maxing out now. And notice where the weight is. Exactly horizontal, as far as it can be, and that's the maximum tension. When the weight is the maximum distance from the pivot. Now if I keep going, now I've gone past it. Now it's getting up towards the top, and notice the amount of tension is going down, going down, going down. It's getting very, very close to zero, and that's getting very close to the top. When that's at the very top, and that's about as far as I'm going to go, because otherwise it's going to run over here the other side, this would go to zero. Okay? Now let's go ahead and we'll put that down to a certain point. Where? Doesn't really matter. We'll use that point. Okay, so now I've set it up. It's now in static equilibrium, which means that the force this direction, the torque this way and the torque that way are equal. And the torque here, the tension here is 4.4. Each one of those little dashes is 2. But I also am going to have to measure the radius here in a second of that wheel. And the mass is a 500 gram mass, which I'm going to do this analysis on paper here in a little bit on the computer. I think would be easier for you to see. Actually, hold on. All right, now we're here to measure the radius. And it goes from the pivot down there to the bottom of the wheel because there's a groove, which sure looks like, let me get it in the right spot. Again, one-handed is terrible. Right there, okay? Which appears to be around 28 centimeters. And now for the analysis of what we just did. We had a tension out here of 4.4 newtons. We had to measure the radius. Hopefully we did that. The radius from here to here is 28 centimeters. We know this is a 500 gram mass. It's not in the right spot. It's actually over here someplace, but that's fine. And 500 grams equals 0.5 kilograms. And then force of weight equals mg. That's 10, or close enough for what we're doing. There's 5 newtons. And this is going to be pulling down with a force of 5 newtons. Well, if the whole thing is not rotating, then it's at equilibrium, which means the torque of the string equals the torque of the mass. The torque of the string will be the force times the perpendicular distance. Over here, we'll have the force times some sort of perpendicular distance. And when we calculate that, I get that gives me the perpendicular distance, the moment arm, to be, I got 0.246. Yes, which again, we're not that exact, which is about 25 centimeters. That says that when I go back to the lab, that the distance from the axle to right above the mass should be 25 centimeters. Again, the mass is actually over here. Let's go see that. And notice, after what we just calculated, it's going to work out. Notice there's the 0 mark in the center. And over here, there's 25. And what is right below 25? The mass, which proves that the mass is 25. The line of force of the mass is 25 centimeters from the pivot, which proves the concept of moment arm.